In this video, we're going to look at integrating polar equations with the TI-84 and how to do that, specifically definite integrals. These definite integrals came up in the lecture on how to do calculus with polar equations. One of the times they came up was when we were trying to find area of the interior region of a polar graph, r equals a function of theta. That area was given by this formula. I'm not going to go over that in this video. This video is about how to use your calculator to do that. So we're going to jump right in to the example, but that's where one of these examples comes from. So let's find the area of one petal of r equals 4 times cosine of 3 theta. This was example 4 in that lecture on calculus with polar equations. Now, when we did this, we found that the bounds for one petal, one of the options was to go from negative pi over 6 to positive pi over 6, and then we'd integrate the function for cosine of 3 theta, quantity squared with respect to theta, and then multiply by a half. Okay, you can use your calculator to find those bounds as well. We went over that in another video. So I'm not going to do that. I'm just going to do the integration and show you how to do this integration. So we turn to our calculator, and if we're not already in the correct mode, then we're going to force ourselves to be in polar mode. This is one option. So I go into the mode, go down, click on polar, and now I'm ready to go. This is how I tend to do so. And that integration was 1/2 times the integration, so hit math. Down here at number 9 is FNINT, that's my function integration. And then I'm going to go from negative pi over 6 up to positive pi over 6. And then in the interior, we had 4 times cosine of 3 theta. Now, because we're in polar mode, every time I hit the variable key, I'm going to be hitting the theta button. So if I say hit theta, that's just the variable key right here. That'll give me a theta. I want to square that entire quantity and then integrate with respect to theta. So once I hit my variable key. And I get about 4.19, which if I just divide by pi, you can easily see that that's 1 1/3 times pi. So 1 1/3 or 4/3 times pi is what I'm ending up with. Now, one thing I can also do, this is how I prefer to do it in polar mode. I set my calculator to polar mode, and then my variable becomes a theta. If you didn't want to do that, you could have stayed in function mode and just utilized an x every time instead of a theta. So that's another option, and you'll get the same answer, obviously. But either way, you can just use the x in function mode, or you can change your mode to polar, and then every time you hit the variable key, you'll be hitting a theta. So either way is perfectly fine. They'll give you the same answer. When I'm dealing with polar equations, tend to like being in polar mode. And that also helps me with the graphing because I could have graphed that function and looked at it and did some other work as well. Here's another area of the interior region that we found in, well, this was in example 6 of the lecture on calculus with polar equations. So we had the function r equals 3 minus 2 cosine theta, and we found the area of the interior region. This was a limacon, um, dimpled limacon, and the way we found the area of the interior of this dimpled limacon was we took 1/2 integrated from 0 to 2 pi of the quantity 3 minus 2 cosine theta quantity squared. If I wanted to do this in my calculator, again, I prefer to utilize the polar mode. So hit polar, make sure that's in polar mode. And then when I start my calculations, I just hit 1/2 math 9, integrate from 0 to 2 pi. And then be careful that the 3 minus 2 times cosine theta, remember, each time I hit the variable key in polar mode, it comes up as theta. Make sure that whole thing gets squared, or else it'll throw everything off. So make sure the 3 minus 2 cosine theta is all in parentheses being squared. And when I hit this, I get about 34.56, which dividing by pi shows you that that 34.56 is actually 11 pi. So it's 11 pi as your answer. So that's how to integrate with polar. Obviously, interior area was not the only integration that we did. Another way that integration came up was finding arc length. We also found surface area as well. So let me do at least one. In this case, I'll do the arc length. So find the length of one petal of the curve r equals 7 times sine of 5 theta. We actually did this one in example 11 of the lecture. So I will just show you how the setup goes and how to do it on your calculator. So for the arc length setup, we had to find the derivative and then do this square root of the normal function squared plus the derivative squared. And then integrate that. In this case, we had to go from 0 to pi over 5. That would be the length of one petal on that curve. Now, nothing very interesting. Again, I need to make sure I'm in polar mode, which I am. I don't have to, but you can, the easiest way to do it is in polar mode. And then every time I want a theta, I just hit my variable key. Let's go to math and then 9 to integrate. Bottom bound is 0, upper bound is pi over 5. And then I do a square root. Again, square root's the second and then the x squared button. And then I have to make sure I do this correctly. I put parentheses 7 sine of 5 theta. Again, variable button theta. And then I put parentheses around that in my quantity and square it. Make sure the 7 and the sine are both inside the squared. And then inside another parentheses, it's going to be 35 times cosine of 5 theta inside that parentheses and square that. Integrate with respect to theta. Again, I just hit the variable key and I get a theta. When I calculate this, I'll get a nice approximate answer. Here is 14.707 or 71. This is not pi times an integer like the previous couple. This is a more difficult number to express than just like 11 pi or 4/3 times pi, like in the previous examples. So that's it. That's how we integrate using polar coordinates.